All right, so we're in chapter 13 and we just went over some of the corrections like with ANOVA testing. So the Bonferroni corrections, the Holm corrections, and now we are at the bottom of page 14 and we're going to discuss section 13.5.5, which is Tukey's honestly significant difference HSD test. So this is one last post hoc comparison that we want to mention. The author wants to mention this. Again, it's called Tukey's honestly significant difference HSD test. So this is another very popular post hoc test which is used frequently in psychological research, and as we've seen with the Bonferroni adjustment and the Holm correction, the Tukey HSD test compares all possible pairs of group means to determine which ones are significantly different from each other and controls for the family-wise error rate. So it is possible to construct a corresponding confidence interval for the mean using this Tukey's HSD test. The calculations can be quite complicated to do them by hand, so we're not going to get into that in this particular discussion, but for those of you who are interested, the HSD test, it essentially calculates a very critical value, which is based on the studentized range distribution, which takes into account the number of groups and the degrees of freedom for the error term from the ANOVA, right? Your analysis of variance analysis. And so they then go into using the following formula. So for the Tukey's HSD test, the formula here is, let's see, it's Q multiplied by the square root of MSW divided by N. So in this formula, the Q is your critical value from the studentized range distribution. The MSW is your within group mean square value for your overall ANOVA, and N is your sample size for each group. So let's keep going. We're going to go to page 15. So once the HSD value is calculated, it is used to then compare the difference between each pair of group means. Okay, so if the absolute difference between any two group means is greater than the HSD value, the difference is considered statistically significant. So again, JASP will do all of these calculations for you, and the JASP output is interpreted the same as the output for any other hypothesis test, all right? Let's say that one more time. So once the HSD value is calculated, it is used to compare the difference between each pair of your group means. So if the absolute difference between any two group means is greater than the HSD value, the difference is considered statistically significant. So in our JASP software, it's going to do these calculations for us. The JASP output is interpreted the same way as output for any other hypothesis test, and the p-value in the output is adjusted so you can compare it directly to your alpha level. And if you request confidence intervals, okay, these will incorporate the same adjustments. All right, so we're gonna go into section 13.5.6 where we summarize the post hoc analyses using APA style. So it's good practice to select the post hoc test that you want to use before you run it. If you need a post hoc test that is very easy to explain, you may choose the Bonferroni adjustment. If you want a test that is less conservative, the home correction or the Tukey ASD might be a better choice. You may choose and report only one post hoc test. So when you report the results of a post hoc test in APA style, it is common to report the p-value. So here is an example. So post hoc tests using the home correction indicated that joyazepam produced a significantly larger mood change than both anxiety-free, p equals 0.001, and the placebo, p less than 0.001. We found no evidence that anxiety-free performed better than the placebo, p equals 0.150. So the key thing is that you need to indicate which correction you used to adjust the p-values, and of course, I'm assuming that elsewhere in the write-up you have included the relevant descriptive statistics. So for example, the group means, standard deviations, and sample sizes, since these p-values are on their own, which are not terribly informative. All right, so let's see. So what about our assumptions, right? Very important stuff. So we're on page 15. We're in section 13.6. So assumptions of one-way ANOVA. So like any statistical test, analysis of variance relies on some simple assumptions about the data, right? These assumptions will sound pretty familiar once we go through them. And specifically, we're going to have some assumptions about the residuals. So there are three key assumptions that you need to be aware of: normality, homogeneity of variance, and independence. So if you think back to section 13.2.4, we described, or the author described, the statistical models which are underpinning ANOVA in this way. So they said that the null hypothesis equals y ik equals mu plus epsilon ik. And the alternative is that y ik equals the mu of subscript k plus the epsilon of ik, okay? So in these equations, mu refers to a single grand population mean, which is the same for all of our groups, and the mu k is the population mean for the kth group. So up to this point, we've been mostly interested in whether our data are best described in terms of a single grand mean, right, null hypothesis, or in terms of different group-specific means, which would be the alternative hypothesis. This makes sense. So that's actually the important research question. However, all of our testing procedures have implicitly relied on a specific assumption about the residuals. So mu ik, and namely, it relied on a specific assumption such as this, that mu ik is approximately normal, and then in parenthesis 0, comma, sigma squared, or standard deviation squared, close parentheses. So none of the mathematics works properly without doing this section here. So to be precise, you can still do all the calculations and you'll end up with an F statistic, but you have no guarantee that this F statistic actually measures what you think it's measuring, right? That it's reliable. And so any conclusions that you might draw on the basis of the F test might be wrong, okay? So how do we check that, or whether the assumption about the residuals is accurate? So, well, as the author indicated above, there are the 3 distinct claims or assumptions buried in this one statement, okay? So we're going to consider them separately. First, we're going to look at homogeneity of variance. So notice that we've only got the one value for the population standard deviation, right? So our sigma, rather than allowing each group to have its own value or sigma subscript k. This is referred to as the homogeneity of variance or homoscedasticity assumption. So ANOVA assumes that the population standard deviation is the same for all groups, and we're going to talk about this extensively in section 13.6.1. So we're going to move into page 16 and talk about the assumption of normality. So the residuals are assumed to be normally distributed. We can assess this by looking at QQ plots or running a Shapiro-Wilk test. We're going to talk about this more in section 13.6.4. Then we have our third assumption, which is independence. So the independence assumption is a little trickier. What it basically means is that knowing one residual tells you nothing about any other residual, okay? So let's go over that again. So in terms of independence, it is a little bit trickier. And what it basically means is that knowing one residual tells you nothing about any of the other residuals. So all of the epsilon ik values are assumed to have been generated without any regard for or relationship to any of the other ones. There's not an obvious or a simple way to test this, but there are some situations that are clear violations, okay? So for instance, if you have a repeated measures design where each participant in your study appears in more than one condition, then independence does not hold up. So there's a special relationship between some observations, namely those that correspond to the same person. So when that happens, you need to use something like a repeated measures ANOVA, and that's going to come up in section 13.8.1. So now we're going to go through each of these assumptions and we're going to check the assumptions. So we're on page 16, we're in section 13.6.1. So the first thing is we're going to check the homogeneity of variance assumption. So to make the preliminary test on variances, it's pretty much like putting to sea in a rowing boat, basically checking through a rowboat to find out whether conditions are sufficiently calm for an ocean liner to leave port, okay? So there we have our our comparison, okay? So this is from George Box, 1953. So he says, to make the preliminary test on variances, it's rather like putting to sea in a rowing boat to find out whether conditions are sufficiently calm for an ocean liner to leave port. Again, that's George Box, 1953. So there are multiple ways to test the homogeneity of variance assumption. The most commonly used test that the author has seen in the literature would be the Levene test, so Levene, and the closely related, the Brown-Forsyth test. So let's take a look. Okay. So regardless of whether you're doing the standard Levine test or the Brown-Forsyth test, the test statistic is sometimes denoted F, okay? But also sometimes written as W, big W. And it's calculated in exactly the same way that the F test statistic for the regular ANOVA is calculated, just using a ZIK rather than a YIK. So with that in mind, the author is going to give a brief overview of how this Levine test actually works. In real life, you will always use statistical software to check this assumption, right? So we're going to use JASP, but we're just going to go over some brief calculations in the text. So page 16, the Levine test, it's shockingly simple. So suppose we have our outcome variable YIK. All we do is define a new variable, which we're going to call ZIK, corresponding to the absolute deviation from the group mean or average. So ZIK equals the absolute value of YIK minus the mean of Y sub K. All right, so what does this do for us? Well, let's take a moment and think about what ZIK actually is and what we're trying to test. So the value of ZIK is a measure of how the ith observation in the kth group deviates from its group mean. So our null hypothesis is that all groups have the same variance, okay? So for example, the groups have the same overall deviations from the group means. So the null hypothesis in a Levine test is that the population means of Z are identical, okay, for all groups. Got it. So what we need now is a statistical test of the null hypothesis that all group means are identical. So where have we seen this before? So, okay, that's what ANOVA is. And so all that the Levine test does is run an ANOVA on the new variable of ZIK. So then what about the Brown-Forsyth test? Does that do anything particularly different? Nope. The only change from the Levine test is that it constructs the transformed variable Z in a slightly different way, using deviations from the group medians rather than deviations from the group means, okay? So that is for the Brown-Forsyth test, ZIK equals the absolute value of YIK minus median K of Y, where the median K of Y is the median for your group K. So moving on, we're in 13.6.2, so running the Levine test in JASP. So how do we actually run this Levine test? Simple, really. Under the ANOVA assumptions checks option, you can just click homogeneity tests checkbox. So let's go look at that. So we're going to go back in our software here, and we're going to go under, we got to scroll up. We're going to go under assumption checks. And we're going to click homogeneity tests. So this will essentially test the following hypotheses. So the null hypothesis is that all population variances are equal, and the alternative is that not all population variances are equal. So if we look at the output, there it is in the middle under assumption checks. If we look at the output, we can see that the test is non-significant. We got the F value equal to 1.45, and our P value, let's see, is 0.266. Thus, we failed to reject the null hypothesis. There is not evidence that the population variances are not equal. So it looks like the homogeneity of variance assumption is okay. So we're going to move into page 17. And again, we did our Levine test output for the one-way ANOVA and JASP. All right, so that was the assumption check homogeneity test. This author wants to provide a strong word of caution with using the Levine test. So recall that there is a relationship between sample size and statistical power. So if your sample size is large, the Levine test could show a statistically significant effect where your P value is less than 0.05, even when the homogeneity of variance assumption is not violated due to an extent which troubles the robustness of ANOVA. All right, so again, if your sample size is large, the Levine test could show statistical significance even when the homogeneity of variance assumption is not violated to an extent which troubles the robustness of ANOVA. So this was the point that George Box was making in the quote above. Similarly, if your sample size is pretty small, like quite small, then the homogeneity of variance assumption might not be satisfied, and yet a Levine test could be non-significant due to low statistical power. So what this means is that alongside any statistical test of the assumption being met, you should always plot the standard deviation around the means for each group / category in the analysis just to see if they look fairly similar, right? So if there's homogeneity of variance or not. So we're moving into page 17 and section 13.6.3. We're going to be looking at removing the homogeneity of variance assumption. So in our example, the homogeneity of variance assumption turned out to be a pretty safe one. The Levine test came back non-significant, okay? So notwithstanding that, we should also look at the plot of standard deviations, which means we probably don't need to worry too much. However, in real life, we aren't always this lucky. So how do we save our ANOVA when the homogeneity of variance assumption is actually violated, okay? So if you remember from our discussion of t-tests, we have seen this problem before. The student t-test, it assumes equal variances so that the solution was to use the Welch test, which does not. So in fact, Welch in 1951 also showed how we can solve this problem for ANOVA as well. So the Welch one-way test, it's implemented in JASP using the one-way ANOVA analysis. To implement the Welch correction, you simply need to choose Welch under assumption checks. So here, you can click this one. All right. So we see our result, which is displayed also in figure 13.6, which is located on page 17. We're going to check our JASP output against this chart. So let's see, we have our sum of squares, 3.453, degrees of freedom, 2, mean square 1.727 with an F statistic of 18.61 and a p-value of less than 0.001. We see our residuals 1.392, degrees of freedom is 15, mean square 0.093. Then we look at Welch t-test and we see that our drug sum of squares 3.453, degrees of freedom is 2, mean square 1.727, degrees of F-test statistic is 26.32 and the p-value is less than 0.001. With the Welch residuals 1.392, degrees of freedom 9.493, and the mean square 0.147. So again, that is Welch's homogeneity correction as part of our one-way ANOVA analysis using our statistical software JASP. So to understand what's happening here, we have to compare these numbers to what we got earlier in section 13.3. That was when we ran the original ANOVA. So to save trouble of flicking back, this is what we got last time. So we got F2, 15 equals 18.611, p-value less than 0.001. So let's check our F. That's the same. Also shown as none under your homogeneity correction in your output. So originally our ANOVA gave us the result that we just went over. We reviewed that it said F2 15 equals 18.6, whereas the Welch correction gave us F2, 9.49 equals 26.32. All right, so it's different. We're moving to page 18. So then we're going to get into checking the normality assumption. So testing the normality assumption is relatively straightforward. Really, the only thing we need to do is draw a QQ plot. The QQ plot can be produced in JASP by going to assumption checks and checking QQ plot of residuals. And then we should get a graph that looks like figure 13.7. And this graph should look normal. Yeah, it looks good. Let's just scroll down here. So we have standardized residuals and we have theoretical quantiles, and it looks exactly the same. That's our QQ plot produced by JASP. And then we're going to go into this next section on page 18. It's section 13.6.5. So now we want to get into removing the normality assumption with the Kruskal-Wallis test. So now that we've seen how to check for normality, we are led naturally to ask what we can do to address violations of normality. In the context of a one-way ANOVA, the easiest solution is usually just to switch to a non-parametric test. So for example, one that doesn't rely on any particular assumption about the kind of distribution that is involved. So when you only have two groups, the Mann-Whitney or the Wilcoxon test provide the non-parametric alternative that you need. When you've got three or more groups, you can use the Kruskal-Wallis rank sum test, and that's the test that we're going to talk about next. The Kruskal-Wallis test is surprisingly similar to ANOVA in some ways. In ANOVA, we started with the YIK, the value of the outcome variable for the ith person in the kth group. So for the Kruskal-Wallis test, what we'll do is rank order all of these YIK values and conduct the analysis on the ranked data. So let's let RIK refer to the ranking given to the ith member of the kth group. Now let's calculate the mean R subscript K. The average rank given to observations in the kth group would be the following formula. So we have the mean R subscript K equals 1 over N subscript K, and multiply that by the summation of I, multiply that by RIK. So also we can calculate the mean R, the grand mean rank, as the following equation. So this equation involves two summations. So we have the mean of R equals 1 over N, the sum of I times the sum of K times RIK. So now that we have done this, we can then go and calculate the square deviations from the grand mean rank, mean R. So when we do this for the individual scores, if we calculate RIK minus mean of R and then we square that value, what we have is then going to be a non-parametric measure of how far the ikth observation deviates from the grand mean rank. So when we calculate the squared, moving to page 19, the squared deviation of the group means from the grand means, for example, if we calculate the mean R subscript K minus mean R, and we take that value and square it, then what we have is a non-parametric measure of how much the group deviates from the grand mean rank. And with that in mind, we'll follow the same logic that we did with ANOVA and define our ranked sums of squares measures, much like we did earlier. So first we have our total ranked sums of squares. So we have our RSS total, and then that equals the sum of K times the sum of I times RIK minus mean of R, and then we take that value and we square it. So we can define the between groups ranked sums of squares like this. Another really complicated equation, page 19. So now we're looking at the RSSB, which equals the sum of K times the sum of I times the mean of R subscript K minus the mean of R, and then take that value and square it, which goes then to the next row. So RSSB equals the sum of K times the times N of sub K times the mean of R subscript K minus mean of R, and take that value and square it. So if the null hypothesis is true and there are no true group differences at all, you'd expect the between group rank sums, the RSSB, to be really small, much smaller than the total rank sums, the RSS total. Qualitatively, this is very much the same as when we found, when we went about constructing the ANOVA F statistic. But for technical reasons, the Kruskal-Wallis test statistic, usually denoted capital K, is constructed in a slightly different way, so we would actually use this equation. K equals, in parentheses, N minus 1, and then you multiply that by the RSSB divided by the RSS total. And if the null hypothesis is true, then the sampling distribution of K is approximately chi-square with G minus 1 degrees of freedom, where G is your number of groups. The larger the value of K, the less consistent the data are with the null hypothesis. And so then this is a one-sided test. We reject the null hypothesis when K is sufficiently large. So to this point, the author has described the Kruskal-Wallis test, which illustrates the logic and illustrated the logic behind the test. And this is being done at a conceptual level. So this is the right way to think about how this test works. However, from a purely mathematical perspective, it's needlessly complicated. So we're not going to get into showing the deviation, but you can see a bit of algebraic manipulation in the following equation, where k can be rewritten as k equals 12 divided by n minus 1 in parentheses times n. You multiply that by the sum of k, n of k, the mean of r subscript k squared minus 3 times n plus 1. So in this equation that you sometimes will see given for k, this is actually the easier way to calculate k than the other equation described in the other section, but you know, it can be, for a human, it can feel like that equation's kind of meaningless. Maybe a robot, you know, would enjoy it more. It's probably best to think of big K the way that we did describe it earlier, as an analog of ANOVA based on ranks. But keep in mind that the test statistic that gets calculated ends up with a rather different look to it than the one we used in the original ANOVA. Alright, so the story that the author has told us so far, it only actually is true when there are no ties to the raw data. So that means that if there are no two observations that have exactly the same value. So if there are ties, then we have to introduce a correction factor to the calculations, and at this point, the author is assuming that even the most diligent reader probably is going to stop caring, or at least form the opinion that the tie correction factor is something that doesn't require their immediate attention. But we're going to very quickly go through the calculation, omitting tedious details about why it's done this way. So suppose we construct a frequency table for our raw data, and we let little f subscript j be the number of observations that have the jth unique value. This might sound a little bit abstract, so here's our concrete data example from the frequency table of the mood gain from the clinical trial CSV data set. Alright, so we have that, and then we're going to look at this table and notice that the third entry in the frequency table has a value of 2. Since this corresponds to a mood gain of 0.3, this table is telling us that 2 people's mood increased by 0.3. So a little bit more on that point. In the mathematical notation that was introduced above, this is telling us that f subscript 3 equals 2. So now that we know this, the tie correction factor, or TCF, is this equation. TCF equals 1 minus, the numerator is sigma subscript j times f subscript j cubed minus f subscript j, that is the numerator, divided by n cubed minus n. Moving to page 20. So the tie corrected value of the Kruskal-Wallis statistic is obtained by dividing the value of k by this quantity. It is this tie corrected version that JASP actually calculates, and we're finally finished with the theory of the Kruskal-Wallis test. So then we're going to move into section 13.6.6. We're on page 20. So then how do you run this test in JASP? So let's take a look here. We have some directions. Yeah, it does look pretty painless, and it's considered a non-parametric. So using our clinical trials data set, which we have already done our classical ANOVA, and moved mood gain to the dependent variables box and moved drug to the fixed factors box, then we have to look under non-parametrics. All right, it's all the way at the bottom. So here it is. All right. And then we're going to move drug to the box. And then it's going to run the Kruskal-Wallis non-parametric test. Let's take a look. There we go. So at the bottom, we got a test statistic of Kruskal-Wallis test 12.08 with 2 degrees of freedom and a p-value of 0.002. The result should match figure 13.8. So let's take a look. 12.0, they rounded it, yeah, 0.076. All right, so we got it. So that is our Kruskal-Wallis one-way non-parametric ANOVA in JASP. And then, so the test statistic is 12.076 or 12.08 with 2 degrees of freedom. This is actually a chi-square test statistic. The p-value for our test is less than 0.001, which tells us that we should reject the null hypothesis. This means our test is statistically significant. There is evidence of a difference between the drugs. If we wanted to report these results in APA style, we would say a Kruskal-Wallis test showed a statistically significant difference in mood gain between the 3 different treatments. Chi-squared, 2 degrees of freedom equals 8.520. P-value is less than 0.001. 8.52, let me double check. All right, let's keep going. So we're moving into page 21, and let's double check our slides here. So we're at the bottom of this slide deck. So we just ran the Kruskal-Wallis test in JASP. And now we're going to look at the relationship between ANOVA and the student t-test. So we're in section 13.7, page 21. So here's one last thing that the author wants to point out before they finish this discussion of the one-way ANOVA. It's something that a lot of people find surprising, but it's worth knowing about. So an ANOVA with 2 groups is identical to the student t-test. Really, it is. It's not just that they are similar, but they are actually equivalent in every meaningful way. They're not going to get into proving this is true, but they're going to show one single concrete demonstration. So suppose that instead of running an ANOVA on mood gain drug model, instead they're going to do it using therapy as the predictor. So let's go look at this. So we're going to come here and cancel, not save. So we're going to pull up our JASP, and we're going to reload our fictitious data set. run this. And we're going to go to the hamburger here. Okay, and we're going to open recent files, clinical trials. All right. And then, so if we run this as a one-way ANOVA, as shown in figure 13.9, we would get the following results. So we're gonna do ANOVA. Here we go, classical. And so we're looking to put mood gain as our dependent and therapy as our factor. So let's see if we get matching data. Yep, so we got our sum of squares 0.467, 1 degree of freedom, and mean square 0.467 with an F test statistic of 1.708, p-value 0.210, residuals 4.378, 16 degrees of freedom, mean square 0.274. All right, so where's our t-test? Oh, I see. And then they went and they did the independent samples t-test under t-test. Okay, hold on. Classical. And they looked at mood gain as the dependent. And therapy. Oops. And they got, yep, so 1.307, 16 degrees of freedom, and the p-value of 0.210. Okay. Yeah, they look pretty similar. So since we only have two groups, this author is saying they didn't actually need to resort to an ANOVA. They could have just decided to run a student t-test. So they wanted to just show what happened when they just do the student t-test and not the ANOVA. So we can see that what we got in 13.9, and then they're going to show figure 13.10. Let me go check. 13.10. Yep. Okay. So curiously, the p-values are identical for the F-test and the t-test. But what about the test statistic? So having run a t-test instead of the ANOVA, we get a somewhat different answer. So we get that T16 equals 1.307. There is a fairly straightforward relationship here. So if we square the T statistic, then we get the F statistic from what we saw before, which was 1.708. Yep. All right, that's right. This is because the F distribution with one numerator degree of freedom is equivalent to a T distribution with degrees of freedom equal to the denominator degrees of freedom. So let's check. Yeah, I see that. All right, so the next thing that we're going to talk about is going to be the advanced ANOVA. So up to this point, the author has just focused on one way between groups ANOVA, which is used when we have an independent variable with 3 or more levels and an interval or ratio dependent variable. This is ANOVA in its simplest form. In the following sections, we're going to explore some more advanced types of ANOVA. So while we won't delve deeply into each procedure, it is important to introduce them because we are very likely to encounter these methods when looking through when looking through published research, especially within psychology. Okay, so we're at the bottom of page 21, and we are going to go through something called a repeated measures one-way ANOVA, and then we're going to do an example. The one-way repeated measures ANOVA test is a statistical method of testing for significant differences between 3 or more groups where the same participants are used in each group, or each participant is closely matched with participants in other experimental groups. We're at the top of page 22. For this reason, there should always be an equal number of data points in each experimental group. This type of design and analysis can also be called a related ANOVA or a within subjects ANOVA. It is comparable to the paired means t-test that we saw earlier in the course, but now with 3 or more measurements. The logic behind a repeated measures ANOVA is very similar to that of an independent ANOVA, sometimes called a between subjects ANOVA. You may remember that earlier the author showed that in a between subjects ANOVA, total variability is partitioned into between groups variability, or SSB, and within groups variability, or SSW. And after each is divided by the respective degrees of freedom, which gives MSB and MSW. And then we have our F ratio calculated as F equals MSB divided by MSW. So in a repeated measures ANOVA, the F ratio is calculated in a similar way, whereas in an independent ANOVA, the within group variability, or SSW, is used as the basis for the MSW denominator. In a repeated measures ANOVA, the SSW is partitioned into 2 groups. So as we are using the same subjects in each group, we can then remove the variability due to the individual differences between subjects. This is referred to as the SS subjects from the within groups variability. We're not going to go into a lot of technical details about how to do this, but essentially each subject becomes a level of a factor called subjects. The variability in this within subjects factor is then calculated in the same way as any between subjects factor, and then we can subtract SS subjects from SSW to provide a smaller SS error term. So for the independent ANOVA, it would be SS error equals SSW. In a repeated measures ANOVA, it would be SS error equals SSW minus SS subjects. So this change in SS error term often leads to a more powerful statistical test, but this does depend on whether the reduction in the SS error more than compensates for the reduction in degrees of freedom for the error term, as degrees of freedom go from n minus k to n minus 1 times k minus 1. And remember that there are more subjects in the independent ANOVA design. The repeated measures ANOVA, how to do it in JASP, okay? So an example. So first, again, we're going to need some data. So in 1972, Geschwin suggested that the exact nature of a patient's language deficit following a stroke can be used to diagnose the specific region of the brain that has been damaged. So a researcher is concerned with identifying these specific communication difficulties experienced by 6 patients suffering from Broca's aphasia. And as we know, that is a language deficit commonly experienced after a stroke. So we have this table of data. We're on page 22, table 13.2. So this is a table of the number of attempts successfully completed on 3 experimental tasks. So we have 6 participants, and we have our speech, our conceptual, and our syntax. The patients were required to complete 3 word recognition tasks. So on the first speech production task, patients were required to repeat single words read aloud by the researcher. And on the second conceptual task, it was designed to test word comprehension. Patients were required to match a series of pictures with their correct name. And then on the third, the syntax task, this task was designed to test knowledge of correct word order. Patients were, moving to page 23, patients were asked to reorder syntactically incorrect sentences. Each patient completed all 3 tasks. The order in which patients attempted the tasks was counterbalanced between participants. So each task consisted of a series of 10 attempts. The number of attempts successfully completed by each patient are shown in table 13.2. You will find that these data are in the Broca CSV file, which you can load into JASP. And so it looks like we're going to need that. So let's go get it. I don't think we have that anywhere. So we need our GitHub Faulkenberry JASP data. I think we can get it from here. JASP book. Go into data and let's see. We're going to pull the Broca CSV file. Here it is. All right, I need to go to the other. Hmm. I may not be able to access this one from here. But that's okay. So for now, we're just going to look at, we're going to read through this example and we'll try to find that data set later. So to conduct the one-way, okay, we could also maybe do an example for the clinical trials data set, but they're just going to walk us through how to do a repeated measures one-way ANOVA. So you go into ANOVA and you would go into classical, okay, and then repeated measures this time. And there's the repeated measures factors box under the RM factor 1. You add level 3. Optionally, in the repeated measures factors box, you can update RM factor 1 to something more meaningful. And so for the Broca's file, they changed the name to task. Then they moved speed and conceptual and syntax to the repeated measure cells as level 1, level 2, and level 3 respectively. So we're just going to take a look at what it looks like. And then under assumption checks, they checked the box next to sphericity tests, and they got some interesting looking output. Okay, so I'm just going to read it to you. So for repeated measures ANOVA, there's 3 tables. The first table is the within subjects effects, and so we have our task and our residuals. We have sum of squares 24.778, residual 17.889. We have our degrees of freedom, we have our F-test statistic, and we have a p-value of 0.013. Underneath that, within subjects, we have our between subjects effects. This lists our residuals as sum of squares with 5 degrees of freedom. Mean square is listed. There's no F-test statistic or p-value in that table. Then we have our assumption checks at the bottom, and so we can see for our task and our p-values, and we have a whole bunch of statistics there. So let's keep reading here. We're at the bottom of page 23. We did the repeated measures example in the textbook, chapter 13. And before looking at the results of our repeated measures ANOVA, we could take a look at Mauchly's test of sphericity, which tests the hypothesis that the variances of the differences between the conditions are equal, which means that the spread of difference scores between the study conditions is approximately the same. So in figure 13.11, Mauchly's test significance level is p equals 0.720. If Mauchly's test is non-significant, like p is greater than 0.05, as is the case in this analysis, then it's reasonable to conclude that the variances of the differences are not statistically significant. So for example, they are roughly equal and sphericity can be assumed. If on the other hand, Mauchly's test had been significant, which is your p-value is less than 0.05, then we would conclude that there are significant differences between the variance of the differences and the requirement of sphericity has not been met. In this case, we're going to apply a correction to the F value that was obtained. And let's go back here. So we're going to apply a correction to the F value obtained in the one-way related ANOVA analysis. So in the greenhouse geyser value in the test of sphericity table, if the greenhouse geyser value in the test of sphericity table is greater than 0.75, you should use the Hune-Felt correction. If the greenhouse geyser value is less than 0.75, you should use the greenhouse geyser correction. So in JASP, both of these corrected F values can be specified in the sphericity corrections checkboxes under the assumptions check options. And the corrected F values are then shown in the results table. So we can see on page 24, we have our figure 13.12. It is the one-way repeated measures ANOVA output, and it is the test of within subjects effects. So we can see all that. We can see our sum of squares, our sphericity corrections, our degrees of freedom, mean square, F-test, statistic, and p-value. So in the analysis we saw that the p-value for the Mauchly's test of sphericity is greater than 0.05. It was 0.720. So that meant that we could assume that the requirement of sphericity had been met, so no correction to the F value was needed. So we could use the non-sphericity correction output values for the repeated measure task. We have an F-test statistic with 2 degrees of freedom of 6.925 and a p-value of 0.013. This test is statistically significant at the standard 0.05 alpha level, so we would report it as this. The number of tests successfully completed on each language task, they did vary significantly depending on whether the task was speech or comprehension or syntax based. F2, 10 equals 6.93, P equals 0.013. Post hoc test analysis can also be specified in JASP for repeated measures ANOVA in the same way as for independent ANOVA. The results are shown in figure 13.13. We're still on page 24. So we can see this post hoc comparison analysis and output. This output is indicating that with the Holm correction, none of the pairwise comparisons are statistically significant at the standard 0.05 alpha level. So we can see level 1 and level 2, and then level 2 and level 3. We have our mean difference, our SE, degrees of freedom, t-test statistic, and the p-Holm correction. So as usual, Descriptive statistics should be reviewed to help interpret the results. One particularly nice way to produce them in the JASP output is to go to the marginal means menu and move task to the box on the right. This will produce the table which is shown in figure 13.14, which includes not only means for each condition but also 95% confidence intervals for each. We're on page 25. Comparison of the mean number of trials successfully completed by participants shows that Broca's aphasics perform reasonably well on speech production, M equals 7.167, and language comprehension tasks, M equals 61.167. However, their performance was considerably worse on syntax. That task, M equals 4.333, with a significant difference in post hoc tests between speech and syntax test performance. So we have our table, marginal means for tasks with 95% confidence. All right, and that is the marginal means for the repeated measures ANOVA. Next, we're going to look at the Friedman non-parametric repeated measures ANOVA test. So the Friedman test is, again, a non-parametric version of a repeated measures ANOVA and can be used instead of the Kruskal-Wallis test when testing for differences between 3 or more groups where the same participants are in each group, or each participant is closely matched with participants in other conditions. If the dependent variable is ordinal scale, or if the assumption of normality is not met, then the Friedman test can be used. So as with the Kruskal-Wallis test, the underlying mathematics is very complicated. We're not going to go into it here. We're just going to allow the software to calculate the tie-correlated version of the Friedman test. And in figure 13.15, we have an example using the Broca's aphasia data that we have already looked at. It is pretty straightforward to run a Friedman test in JASP. Just go to the non-parametrics menu, move task into the RM factor box, and you should also click the Conover's post hoc tests option. So we can see our output right here, page 25, Friedman test and Conover test. The JASP results for figure 13.15 show a chi-square value, degrees of freedom, p-value, Kendall's w-value. Since the p-value is less than the level conventionally used to determine significance, which is the 0.05, we can conclude that there is a difference among the 3 levels of tasks. And in Conover's post hoc tests, they indicate that there is a significant difference between level 1 and 3. Looking back at how we entered the variables into JASP, level 1 was speech and level 3 was syntax. Next, we're moving to page 26, and we're going to talk about factorial ANOVA. So this is another commonly used variation of ANOVA. While a one-way between subjects ANOVA involves one independent variable with 3 or more levels and an interval or ratio dependent variable, a factorial ANOVA includes 2 or more independent variables and an interval ratio dependent variable. So those independent variables are sometimes referred to as factors. A factorial ANOVA with 2 independent variables is sometimes referred to as a two-way ANOVA. So this type of analysis allows us to understand not only the individual effects of each independent variable, but also how they interact with each other in relation to the dependent variable. So in the original version of the text, there is the entire chapter dedicated to factorial ANOVA, and we're also going to be able to check out the link that wasn't working when we checked on it a little while ago, but it's the Tom Faulkenberry GitHub JASP book. And in a factorial ANOVA, we look at two main types of effects. So we look at main effects and interaction effects. A main effect is the effect of one variable at a time, while an interaction effect looks at how the effect of one independent variable may depend on the level of another independent variable. So for this one, it looks like we're able to use that clinical trials data set. The file has two categorical variables, and those are drug and therapy. So if we wanted to look at both of these variables in relation to mood gain, we can do it by using a factorial ANOVA. Our factorial ANOVA would look at the main effect of the drug, the main effect of therapy, and the interaction between drug and therapy. Again, we're not going to get into the heavy math and calculations of the factorial ANOVA, and so we're going to just jump right into interaction effects. So again, what is the interaction effect? So intuitively, the idea is pretty simple. It just means that the effect of factor A is different depending on which level of factor B that we're actually talking about. But what does that actually mean in terms of our data? So we have a plot of figure 13.16, which depicts several different patterns that, although they're quite different to each other, they would all count as an interaction effect. Thus, it's usually not sufficient to say that there is a significant interaction. Researchers should also include an interaction plot. So we have the graphs shown in figure 13.16. They could also show descriptive statistics along with a written description of a specific interaction that is observed. So when interpreting a factorial ANOVA, we often examine the interaction effect before the main effects, because the interaction can provide crucial context for interpreting the main effects. So an interaction effect occurs when the effect of one independent variable on the dependent variable depends on the level of another independent variable. So this essentially means that the relationship between one independent variable and the dependent variable is not consistent across the levels of the other independent variable. So if there is a significant interaction effect, it suggests that the main effects might not tell the whole story. So by examining the interaction effect first, we can avoid misinterpreting the main effects. So if the interaction effect is significant, it indicates that the main effects should be interpreted with caution. The interaction effect helps us understand the conditions under which the main effects hold true. So if the interaction effect is not significant, we can then interpret the main effects with more confidence, knowing that the effects of each independent variable are consistent across the levels of the other independent variable. So here's a quick example of factorial ANOVA using the clinical trials fictitious data set, using both drug and therapy as independent variables, mood gain as dependent variable. So for a full description of these analyses, including a discussion of assumptions, which should be checked before interpreting your results, you can also see the original version of this text. We're going to move to page 27. So on page 27, we have some really nice diagrams. This is figure 13.16, which is showing qualitatively different interactions for a 2x2 ANOVA. So we have a crossover interaction. We have an effect for one level of factor A. We can see where one cell is different, and we can see an effect for one level of factor B. So let's go to page 28 and follow these directions. And we're going to do a factorial ANOVA as well. So let's see. So we went to ANOVA, classical ANOVA. So we need to cancel out of this. Open recent clinical trial data. We're going to go to the top here under ANOVA. Okay. We're going to go to classical. We're going to move mood gain into the dependent variables. We're going to move drug and therapy to fixed factors. Okay. We're going to go down and check the box next to estimates of effect size. And we're going to uncheck the default, and we're going to check this one and the partial. Okay. Then we're going to go under descriptive plots. There it is. And then we're going to move therapy to the horizontal lines. And drug to the separate lines. And that's how we're going to make these plots. The results, again, should match figures 13.17 and 13.18. Let's take a look. So, yep, that looks good. And then we're going to check our data on the top here. So we have our data, it matches our factors. We have our F-test statistics, our p-values. Okay, looks good. So it's saying here that first we should consider whether there is an interaction effect. So looking at the interaction plot, it looks like the effective therapy is relatively similar for joyzepam and placebo. We know this because the slope of the lines for these two treatments is similar. This means the effective therapy was similar. For the anxiety-free, the line has a slightly steeper slope. Which means that the impact of cognitive behavioral therapy versus no therapy may have been greater. It is a small difference, and when we look at the output for the factorial ANOVA, we see that the interaction effect is not statistically significant. So let's look at that. We have our interaction plot, we have our output. This is the factorial ANOVA. We're moving to page 29. So now that we know that there is no significant interaction effect, we can consider the main effects. So from figure 13.18, we see that there is a statistically significant main effect of therapy. This one is less than 0.05. So that would be reported as F1, 2. Actually, we want to report it with the therapy and residuals. So F1, F1, 12 equals 8.58. P-value equals 0.013. There is also a statistically significant main effect of drug. So look at that line. So that is the F2, 12 equals 31.71, and the p-value is less than 0.001. So at this point, we know that there is not a significant interaction effect, but there are significant main effects. So just as we saw with the one-way ANOVAs, the next step would be to look at the descriptive statistics and conduct the post hoc test to determine which groups are different. So we could, we could do a Tukey, a Bonferroni, a Halm correction. Those are all options in the software. And the last thing that the author wants to explain in relation to the factorial ANOVA is effect size. So we may have noticed that the output in figure 13.18 has that column second from the end that has the 0.096, 0.713, 0.056. So let's take a look here. So we saw a similar column when we learned about the one-way ANOVA. And in the next column over, we see a similar variable, but it has a subscript little p, which stands for partial. So just as we saw with the one-way ANOVA, we have the variable that is the proportion of total variance that can be attributed to that factor. So if we're considering factor A, then it would be SSA divided by SS total. Just like we saw originally, this can be interpreted in pretty much the same way as the R squared in regression, linear regression. It tells you the proportion of variance in the dependent variable. That can be accounted for by the main effect of factor A. It is therefore a number that ranges from 0, which is no effect at all, to 1, which would say it accounts for all of the variability in the outcome. Moreover, The sum of all of these values taken across all the terms in the model will sum to the total R squared for the ANOVA model. So if, for instance, the ANOVA model fits perfectly, like there is no within groups variability at all, then these values in our second column from the right will sum to 1. Of course, that rarely, if ever, happens in real life. However, when you're doing a factorial ANOVA, there is a second measure of effect size that people like to report. So this is what's shown in the second column from the right. And then in the partial column, which is the rightmost column, in this column, when measuring the effect size for a particular term, say the main effective factor A, you actually want to deliberately ignore the other effects in your model. So for example, the main effective factor B. That is, you would pretend that the effect of all these other terms is 0, and then calculate what the value would have been. This is actually pretty easy to calculate, and all you have to do is remove the sum of squares that's associated with the other terms from the denominator. So in other words, if you want the partial for the main effective factor A, the denominator is just the sum of the sum of squares values for factor A and the residuals. You can see that on page 29 as well. This will give you a larger number, which the cynic in the author suspects accounts for the popularity of the partial value. Once again, you always get a number between 0 and 1, where 0 represents no effect. However, it is slightly trickier to interpret what a partial value means. In particular, you can't actually compare the partial values across terms. So suppose, for instance, there is no within groups variability at all. If so, the SSR equals 0. What that means is that every term has a partial value of 1, but that doesn't mean that all terms in your model are equally important, or indeed that they are equally large. All it means is that all terms in your model have effect sizes that are large relative to the residual variation. It is not comparable across terms. All right, so we're moving to the bottom of page 29. And let's take a look. So we have our analysis of covariance. We're in section 13.8.3. So analysis of covariance and COVA is a variation of the ANOVA that is used when you have an additional interval or ratio variable that you think might be related to the dependent variable. So this additional variable can be added to the analysis as a covariate. So hold on, we have a typo here. So we have our analysis of covariance, and then we have our covariate again. A covariate is a variable that is not of primary interest but is included in an analysis to control for its potential influences on the dependent variable. So in ANCOVA, the values of the dependent variable are adjusted for the influence of the covariate. And then the adjusted means are tested between groups in the usual way. This technique can increase the precision of an experiment and therefore provide a more powerful test of the equality of group means and the dependent variable. So how does the ANCOVA do this? So although the ANCOVA, although the covariate itself is typically not of any experimental interest, adjustment for the covariate can actually decrease the estimate of experimental error, and thus by reducing error variance, then you increase precision. So this means that an inappropriate failure to reject the null hypothesis, like a false negative or a type 2 error, is likely. So again, this means that an inappropriate failure to reject the null hypothesis is less likely. So despite this advantage, ANCOVA runs the risk of undoing your real differences between groups, and this should be avoided. So we're going to take a peek at figure 13.19, which is on page 30. So when we look at this example, it shows a plot of statistics anxiety against age and shows two distinct groups. So the students who have either an arts or science background or preference, so ANCOVA with age as a covariate might lead to the conclusion that statistics anxiety does not differ in the two groups. So do we think that this conclusion would be reasonable? Honestly, probably not, because the ages of the two groups do not overlap, and analysis of variance has essentially extrapolated into a region with no data. Again, this is a plot of statistics anxiety against age for the groups of scientists and artists. So clearly you need to practice very careful, mindful thought when you are doing the ANCOVA. So careful thought needs to be given to the analysis of covariance with your distinct groups. This applies to both one-way and factorial designs, as the ANCOVA can be used with both. We're going to do a really quick example of an ANCOVA. We're not going to get into great detail with the formulas or assumptions, but because this is a procedure that you're likely to come across when you're reading psychological research articles, the author does think that it is important to just walk through a basic one example of how to interpret the results of the ANCOVA. So it says here that there's a health psychologist that was interested in the effect of routine cycling and stress on happiness levels, with age as a covariate. So you can find this data set in the Tom Faulkenberry GitHub for JASP. And in this ANCOVA CSV file, stress and commute are the independent variables or factors, and the dependent variable is happiness. The covariate is age. Okay, let's take a look. So let's see if we can actually grab that data. The link was broken before, but we'll try again. So we're gonna go to here. tomfalkenberry.github.io. Let's try. Hold on. Sometimes it works and sometimes it doesn't. But let's try to open it up here. Data sets. There's a zip file and a repository. Let's try this again. So we had a couple data files of Broca. We got that one this time. And then we got this one. Go back to page 30 of Ankova. Okay. Let's try to get this Ankova file here. Save. All right, so we're gonna go back to JASP. And we're gonna open this. And we're going to open up Ankova. Downloads. Ankova. Open. There we go. We're gonna go under ANOVA. We're gonna select Ankova. We're gonna move happiness to the dependent variables box. And we're gonna move stress and commute to the fixed factors. Okay. Move age to the covariate box. And then we're gonna check the boxes down here under our estimates of effect size. Okay. We're going to uncheck the default and check these two. And then we're going to go under descriptive plots. Descriptive plots. And we're going to move stress to the horizontal axis. And we're going to move commute to the separate lines. And we're going to let's see. We're going to go under marginal means here. And we're going to move stress and commute to that box. Stress plus, or stress star here. And we're going to take a look at this data. All right, that looks nice. So let's interpret it. So the results should match figure 13.20, which is on page 31. So let's look at the top. So we have Ankova Happiness, we're looking at stress, commute, age. So we have 2751. We're looking here. 2751.5, 2213.9, 334.4, 740.1, 784.4. We have our degrees of freedom, we have our mean squares, we have our F-test statistics. All looks good. Our p-values, and we have these two funky ones over here. It looks like it completely matches, which is great. All right. And then let's keep looking. In the middle, we have our descriptive plots, which look like they match as well, high to low, 30 to 90. And then we have down on the bottom, marginal means. So we can blow that up too. So we have 43.58, 85.82, 36.11, 51.089. Looks like all that is matching nicely. Okay. So we have figure 13.20. It's the factorial ANCOVA conducted in JASP using the ANCOVA data set. So we're going to interpret the output that we see here. So we have our F value for the covariate age. It is significant at p equals 0.023. So let's double check age. 0.023, yes, it's significant. This suggests that age is an important predictor of the dependent variable happiness. When we look at the estimated marginal mean scores, adjustments were made compared to an analysis without the covariate because of the inclusion of the covariate age in this ANCOVA. An interaction plot, as shown in the middle, is a great way to visualize and interpret these significant effects. Then we can look at the interaction effect between these factors. There is a statistically significant interaction between stress and commuting method. So let's take a look. So here it is F1,15 and then equals 14. Let's double check. Yeah, 14.15, p-value 0.002. Referring back to the interaction plot, for people who cycle to work, the difference in happiness between those with high and low stress is larger than the difference for those who drive to work. Given the nature of the interaction, this is a case where we may also want to examine the main effects. There is a significant main effect of stress, all right? So let's take a look at that. F1,15 equals 52.61. Let's look at stress. Yep, and it's significant, okay? P-value 0.001. There's also a significant main effect of commute. So let's look at commute. F115 equals 42.33. Let's see. Yes, I see it. P-value 0.001. So as with the other ANCOVA methods we've seen, ANOVA methods we've seen, in the ANCOVA, effect size can be measured as well, and so we can look over here. So this these two values measure effect size. Remember, the closer they are to 1, right, the greater the effect size. Then we're going to just briefly get into the last topic, which is the Mann-Cova. So we did Mann-Cova, and now we're going to do the multivariate analysis of variance, or a Mann-Cova. All right, so we're on the bottom of page 31. There is just this one last form of ANOVA that we're going to cover in this chapter, the multivariate analysis of variance. Not Mann-Cova, it's just MANOVA. I have a typo here. There's ANOVA and MANOVA. So save it, change. There we go. So we have the multivariate analysis of variance, the MANOVA. This is just one last form of ANOVA that we're going to cover in this chapter. The multivariate analysis of variance, the MANOVA, is an extension of the ANOVA that allows researchers to examine the effects of one or more independent variables on multiple dependent variables simultaneously. So this technique is particularly useful in psychological research, where multiple related outcomes are often measured. For example, psychological scales are often comprised of several subscales. So a MANOVA can look at all of the subscales at the same time. By considering multiple dependent variables simultaneously, the multivariate analysis of variance, the MANOVA, can detect whether the independent variables have a significant effect on the combination of dependent variables. Moving to page 32. This approach provides a more comprehensive understanding of the data compared to conducting separate ANOVAs for each independent variable. Separate ANOVAs for each dependent variable, right, for each outcome. There are several reasons why researchers might choose to use a MANOVA. First, it helps control for type 1 error. So risk of finding a false positive result. Conducting multiple ANOVAs increases this risk, but MANOVA reduces it by analyzing all dependent variables together. Second, MANOVA can detect multivariate effects that might not be apparent when looking at each independent variable separately. By considering the relationships between dependent variables, MANOVA provides a more holistic view of the data. Third, MANOVA is particularly useful for understanding complex relationships in psychological research where multiple related outcomes are often of interest. So the steps for conducting the MANOVA are similar to those for ANOVA, with some additional considerations for the multivariate nature of the analysis. MANOVA has several assumptions, including multivariate normality, homogeneity of variance, covariance matrices, and the absence of multicollinearity among dependent variables. Researchers should check these assumptions before they proceed with the MANOVA analysis. One of the most commonly used test statistics in MANOVA is the Wilks lambda, which tests the null hypothesis that the independent variables have no effect on the combination of dependent variables. A significant Wilks lambda indicates that the independent variables have a significant multivariate effect. If the MANOVA reveals significant effects, researchers can conduct post hoc tests to explore which specific dependent variables are affected by the independent variables. These tests help to interpret the multivariate results in more detail. When interpreting the results of MANOVA, it is important to consider both the multivariate effects and the individual effects of each dependent variable. Significant multivariate effects indicate that the independent variables have a combined impact on the dependent variables. Researchers should also examine the results of post hoc tests to understand how each dependent variable is influenced. This approach ensures that the conclusions that are drawn from the analysis are accurate and reflect the true nature of the relationships between the variables. MANOVA is a powerful statistical tool, and it allows researchers to analyze multiple dependent variables simultaneously. By considering the relationships between dependent variables, MANOVA provides a more comprehensive understanding of the data, and it helps to uncover complex effects that might not be apparent with separate ANOVAs. This technique is particularly valuable in psychological research, where multiple related outcomes are often of interest. All right. Summary. So there is a fair bit that was covered in this chapter. And there is a lot that is not that was not covered in this chapter. The original version of this textbook devotes 2 chapters to ANOVA. The author recommends checking out the original textbook if you would like more work to be done and a more thorough introduction to ANOVA, particularly with the factorial ANOVA that we quickly ran through in section 13.8.2. We're actually going to go back and do that one since I have the data set. In terms of what we have discussed in this chapter, the key topics were the basic logic behind how ANOVA works and how to run it in JASP, how to compute and effect size for ANOVA, post hoc analysis and corrections for multiple testing, assumptions made by ANOVA, how to check the homogeneity of variance assumption and what to do if it is violated, how to check the normality assumption and what to do if it is violated, repeated measures ANOVA and the non-parametric equivalent, the Friedman test, factorial ANOVA, which are ANOVA with 2 more independent variables, also known as factors, analysis of covariance or ANCOVA, which adds a covariate to a one-way or factorial ANOVA, multivariate analysis of variance MANOVA, which are ANCOVA with 2 or more dependent variables. Understanding these various forms of ANOVA is crucial for being able to interpret results of psychological research. Each type of ANOVA, it serves a specific purpose and is suited to different research designs and questions. By mastering these techniques, you will be better equipped to interpret complex analyses and draw meaningful conclusions. With all chapters in this version of the JASP textbook, there are numerous sources that are going to be cited. The standout text that has most heavily influenced this particular chapter is Sahai and Aguil from 2000, While it may not be ideal for an introductory lesson, it is an excellent resource for advanced statisticians interested in understanding all of the mathematics behind ANOVA. So we're actually just going to quickly run back to one section that we didn't have our data for. So we're going to run through the ANCOVA data. And we're going to use actually it was the BROCAs. Let's go back there. So we're on page 23. We went back 10 pages. And we are going to do the repeated measures one-way ANOVA example, since we now have the BROCA's data set. This was pretty complicated, so we want to make sure we have the visual. So here we go. We're going to grab the recently downloaded file. Downloads, BROCA, open. Here we go. So we're going to go back and conduct the one-way repeated measures ANOVA in JASP using the 3 variables in the BROCA CSV file. So we go to ANOVA and we go to repeated measures. And then in the repeated measures factors box, we can add the level 3. All right, and then okay. So we're going to let's see, RM factor 1. So we can actually update this as well to say task, which is pretty cool that you can update that. Oops. So we updated and added a 3rd level and updated that to be task. Then we're going to move speed, conceptual, and syntax to the repeated measure cells as level 1, 2, and 3. So speech, and then conceptual, speech, conceptual, and syntax. There we go. Okay, we're getting our output. And then we're going to go to assumptions checks. And we're going to check sphericity tests. So this is definitely something different, right? Then we're going to check our output against figure 13.11 on page 23. So that looks the same. We added the sphericity tests. What's the output looking like? So for the top chart, we have three charts. We have our task and our sum of squares, our residuals, our mean square, our F statistic of 6.9, and our p-value of 0.013, our residuals, and we have in the middle chart we have sum of squares, 5 degrees of freedom, mean square, and then in the bottom we have our assumption checks. So this is where we got this Malkley's W, the approximate chi-square, degrees of freedom, p-value, and then the greenhouse geyser and the Hunefeld. All right, so let's go through this and then we'll be done. So again, before we look at our results, we want to take a look at the Malkley's test of sphericity, which tests the hypothesis that the variances of the differences between the conditions are equal, right? This means the spread of differences, the spread of different scores between the study conditions is approximately the same. So Malkley's test significance level is the significance level for the Malkley's test is 0.720. So if Malkley's test is not significant, right, if it's greater than 0.05, as is the case with this analysis, then it is reasonable to conclude that the variances of the differences are not significantly different, right? So then they are roughly equal and sphericity could be assumed. If on the other hand, the test had been significant for Malkley's test, p less than 0.05, we would conclude that there are significant differences between the variance of the differences and the requirement of sphericity would not have been met. So in this case, to summarize, we should apply a correction to the F value obtained in the one-way related ANOVA analysis. So if the greenhouse geyser value test of sphericity table is greater than 0.75, which it is, then you should use the Hunefeld correction, all right? But if the greenhouse geyser value is less than 0.75, then you would use the greenhouse geyser correction. So in JASP, both these corrected F values can be specified in the sphericity corrections check boxes under the assumptions checks options, and the corrected F values are shown in the results table. So let's take a look. I see in the textbook figure 13.12, which is pretty nice. This is the within subjects effects. So let me make sure we got the same. Yeah, we did. So in our analysis, we saw that the p-value for the Malkley's test of sphericity was not significant. So we assume that the requirement of sphericity has not been met. Oops. Hold on. So this assumes the requirement of sphericity has been met. So no correction to the F value would be needed. Therefore, we can use the non-sphericity correction, which we are using it. So we can see that none is selected here. But if we also want to add these just to copy the book, we can add all of it to the top, and then our data would match, right? None, greenhouse geyser, and hewn felt. Yep, so this matches now. Okay, and then let's keep looking through this example. So sphericity, we can use the non-sphericity correction output values for the repeated measure task, which we have. We have an F-test statistic with 2 degrees of freedom here on the top. And it's 6.925. P-value 0.013. This test is statistically significant at the standard 0.05 alpha level, so we would say this. The number of tests successfully completed on each language task, they did vary significantly depending on whether the task was speech, comprehension, or syntax-based. F2, 10 equals 6.93. P equals 0.013. Okay. Post hoc test analysis can also be specified in JASP for repeated measures ANOVA in the same way as for independent ANOVA. We have some results shown in figure 13.13 in the text. This output indicates that with the home correction, again, this is under the post hoc, so we can add this. And we did the Helm effect size. You see. Post hoc for tasks. Yep, here we go. Move this over. We should get the same levels data. So we got our levels data on the bottom, post hoc tests, post hoc comparisons task, level 1, level 2, 1.00, 0.683, 5, 1.464, 0.203, level 3, 2.833, 0.910, 5, 3.114, 0.079, level 2, 3, 1.833, 0.703, 5, 2.607, 0.096. So that's the figure 13.13 post hoc tests and repeated measures, ANOVA and JASP. So as usual, descriptive statistics should be reviewed to help interpret the results. One particularly nice way to produce them in JASP is to go to the marginal means menu and move task to the box on the right. All right, this will produce this table shown in figure 13.14. So hold on, we're going to do the marginal means. To get this other table. Let's check this one. So 13.14, level 1, 2, 3, and 7.167, 6.167, 4.333. We have 95% confidence in our SE values. So this table includes not only means for each condition, but also the 95% confidence intervals for each mean. Comparison of the mean number of trials successfully completed by participants shows that Broca's aphasics perform reasonably well on speech production, and then the M equals 7.167. Language comprehension, M equals 6.167 tasks. However, performance was considerably worse on the syntax task, M equals 4.33, with a significant difference in post hoc tests between speech and syntax task performance. Then in the next section, we have the Friedman non-parametric repeated measures ANOVA. So again, this Friedman test is a non-parametric version of a repeated measures ANOVA, can be used instead of the Kruskal-Wallis test when testing for differences between 3 or more groups where the same participants are in each group, or each participant is closely matched with participants in other conditions. If the dependent variable is ordinal, or if the assumption of normality is not met, then the Friedman test can be used. So as with the Kruskal-Wallis test, the underlying math is very complicated, so we're not going to get into it. For the purposes of this instruction, it is sufficient to notice that JASP calculates the tie-corrected version of the Friedman test. So we can see figure 13.15. It's an example using the Broca's aphasia data that we have already looked at, and it's pretty straightforward to run a Friedman test in JASP. We go to the non-parametrics menu at the bottom. Okay, right here. And we move task into the factors box. And then we check the Conover's post hoc tests. And we take a look. All right, so then we get the Kendall's W of 0.553, our p-value 0.036, degrees of freedom, chi-squared, all right, 6.636. We get our Conover's test in the bottom. So we have our level and our t-statistic 1.441, 10 degrees of freedom. And we have our WI, WJ, RRB, p-value, and the Bonferroni and the Holm looks good. So again, the JASP gives us our output, which matches figure 13.15 on page 25, showing the chi-square value, degrees of freedom, p-value, and a Kendall's W. Since the p-value is less than the level conventionally used to determine significance, we can conclude that there is a difference among the 3 levels of task. And Conover's post hoc tests indicate that there is a significant difference between level 1 and level 3. So let's take a look. All right, and looks good. So that is the bottom of page 25, and we figured out how to get all of the data out of the Broca's task example. And that is going to conclude chapter 13 on ANOVA, analysis of variance.